For any newcomers here, Science in the News is a graduate student volunteer organization whose core mission is to bridge the communication gap between scientists and the general public. So we work to train scientists to communicate their research in a way that's accessible and exciting. And we also give community members, you guys, the opportunity to learn about what hopefully you guys will think is some really cool science, really at the cutting edge of what's going on. So, one thing I would like to mention before I move into introducing our speaker, you will see on the schedule, if you have one of these cards, that there was originally a lecture scheduled for November 13th. Unfortunately, that has had to be canceled. So we will wrap up the fall lecture series by coming back on November 20th with our final fall series lecture, which will be using machine learning to diagnose neurodegenerative diseases. And then hopefully within the next few weeks, we'll have our spring schedule online, so you guys can start taking a peek on that. Those spring seminars are going to be held same time, same room, just starting, I think, end of February through middle of April.
Here, because content used to be all at
This year, we're keeping it all here.
Okay.
We got other comments? Cool. All right, so then, without further ado, I will introduce today's speaker, Linda Xu, who is going to present on the many magnitudes of darkness, the long and multifaceted search for dark matter. Linda pursued her bachelor's and PhD in physics at MIT and Harvard, respectively, and currently works at the intersection of particle theory, cosmology, and astrophysics. So, because I cannot dig any deeper into any of those words, I will immediately turn it over to Linda and let her impress you with what she's got lined up for you today.
All right, thank you very much. Hello, everyone. My name is Linda, and I work on dark matter, and I would like to talk to you about dark matter. So let's start. How many of you have heard of the phrase dark matter before? How many of you know what dark matter is? It's great, because I have no idea. Let's talk about it. Okay, so the structure of the talk is roughly going to go like this. We're going to talk about the basics and roughly the history of the discovery of dark matter, and then we're going to talk about one model in a lot of detail, and then a bunch of models in less detail. And I'm framing everything around the central questions of what is dark matter and how we would detect it. A theorist's question and an experimentalist's question. Okay, so what is dark matter? I will tell you pretty much everything that I know, which is it is matter, which means it is heavy and responds to gravity, and it is dark, which means it doesn't interact with light, and I'll come back to this one in a sec. And the last thing I know about it is that it is everywhere, and there's a large amount of it. It constitutes over 85% of the matter budget of the universe, and the other 15% is everything else that we know about tables and chairs and us. There's a lot of it up there. Okay. So what exactly do I mean when I say that it doesn't interact with light? Well, let's start with interact. When I say a particle interacts with light, I'm talking about two specific types of interactions. A particle interacting with light means that a particle can absorb light, and a particle can emit light. Since light is electromagnetic energy, the statement that a particle interacts with light is a statement that a particle can absorb and emit electromagnetic energy. And with these two processes, absorbing and emitting light, you can compose these to make pretty much anything else that we see. This is a light bouncing off of a particle, which is a particle absorbing and then emitting light. And this is responsible for the fact that we can see anything. Light comes, bounces off that chair, and then bounces to my eyes, which is why I can see the chair. So the statement that dark matter doesn't interact with light is the statement that dark matter light cannot bounce off dark matter and then bounce into my eyes, and therefore I can't see But this is a much stronger statement than just me not being able to see dark matter. Because there are a lot of other things that we can't see. Like, we can't see the air around us, but I am in fact not here to talk about air. So to do that, let's talk about air. Why isn't air dark matter? It is something that has mass. It's made out of chemicals. Chemicals have mass. And it is something that I can't see, right? Okay. But I want to argue that there are ways and situations that exist where we can render gases visible and make the fact that they interact with light explicit. So if any of you guys have been on like a hot road or in a desert, you'll see your vision of the horizon kind of shimmer, or the road will look like it has water on it even though it doesn't. These types of distortions are caused by light bouncing off these air particles and bouncing to us. The fact that the light bounces off air first before coming to us is why we see images that are kind of distorted. And for a more explicit example of being able to see air, anyone who's seen a neon sign, these signs are made by putting a special type of gas, in this case neon gas, into a tube, and you pump it full of electromagnetic energy. You put it in a circuit, and then it will light up. So this is explicitly this type of gas that is normally invisible will emit light. But let's actually talk about this a little bit, because the fact that this specific type of gas specifically gives off red light is a very important feature and one that we will be using to talk about dark matter. Okay, so light given off by light bulbs, the light in this room, the light from the sun is white, right? Like it's yellowish white, but it's white. If any of you have seen a prism before, if you put a prism up to this type of light, you will find that a rainbow comes out of it. So this type of white light that is given up by light bulbs and the sun is composed of a lot of different colors. And since light is electromagnetic energy, each of these colors actually represents a different amount of energy. Purple is more energetic, red is less energetic. And the statement that particles, and a feature of our chemical world, the particles that make us up, is that not only can the particles that make us up absorb and emit electromagnetic energy carried by light, it specifically only absorbs and emits electromagnetic energy at specific energies, at specific colors. Each chemical substance has a specific set of colors that it will absorb and emit to. That's why neon is specifically red. And this, because it's a unique set of colors, is now a fingerprint we can use to identify a substance that we don't specifically know anything about. We can use the set of colors that it preferentially absorbs or emits to identify an unknown substance. So this is what the experiment would look like. I have a gas cloud. I can't see it, but it's in a box, okay? And I want to figure out what it's made out of. I do the thing where I shine this light bulb through it and put a prism at the end of it. And what will come out at the other end is, instead of that clean rainbow, I will see that this set of colors has been preferentially absorbed by the gas cloud inside. And then I can look up what chemical this set of color lines corresponds to, and say that, this is nitrogen. I have identified a nitrogen cloud. This way, even though I can't directly see what is inside this box, I can't directly see the gas, I can use its interaction with light to identify and understand it. And this is a property that every chemical substance we know has. So the statement that dark matter doesn't do this is about a lot more than it being invisible. Almost everything that we can experience is an electromagnetic interaction. Like every single sense that we have, the fact that I can touch this table, the fact that I can smell things, obviously the fact that I can see things, all of these are electromagnetic interactions. And this is the same thing as interaction with light. I'm saying both of these a lot. They're the same thing. And everything that we understand, everything that's made out of atoms, has this property. It interacts with light in this way. I can touch it, I can smell it, I can see it. So the statement, and we will call this stuff normal matter, just to have a label for it. And dark matter doesn't, which is a statement that dark matter isn't made out of atoms or molecules. It's not even made out of protons, neutrons, and electrons, the basic building blocks of these particles. It's not made of anything that we are made of. It's also invisible, which makes it hard to find. But this is a strong claim, right? I'm claiming the existence of a particle that is manifestly invisible to me, that I cannot touch or interact with or sense with any of my senses. So, as scientists, the first thing you would ask is, how do I even know it's there, right? How would you even know it's there? Well, here's the only other thing I know about dark matter, is that it's matter, it's heavy, and it responds to gravity. So this is my only chance of figuring out what dark matter is using the fact that it is matter to detect it. The thing is that gravity is very, very weak. Gravity is way, way weaker than electromagnetism. Like I can punch a table and it will hurt, but it takes something the size of the Earth for me to feel the gravity. So I need a large amount of heavy stuff to be able to detect anything gravitationally. If gravity is the only way that I can experience dark matter, I need a large amount of it, and it needs to be very heavy. So where do you find a large amount of very heavy, astronomically heavy stuff? So you go to space. Okay, so let's start a history lesson. This is Vera Rubin. She is quite deservedly often credited for the discovery of dark matter. And what we're going to do today with her is measure the rotation curve of Andromeda. Andromeda is the nearest galaxy to us. It's this particular galaxy. And this is what we're going to do. We're going to measure stars in Andromeda. I've picked out 4 of them over here. And we're going to map out the relationship between the distance of the star to the center of the galaxy and the speed at which it is rotating around the center of the galaxy. Andromeda is a spiral galaxy like the Milky Way. So all of the stars sort of rotate all in this disk that we can see. So all of them are pretty much going in the same direction. And that makes it easy. And why do we care about the rotation velocity? Well, we care about it because the rotation velocity is roughly proportional to the amount of stuff that the star is rotating around over the distance the star is to that stuff. So we're in the solar system, right? The Earth is rotating around the sun. And the sun is the stuff that we're rotating around. So if the sun was very heavy, if this went up, the sun became more heavy, then this rotation velocity would go up. If the sun were way heavier, we would be spinning faster. Conversely, if the sun stayed as it were, but we moved way closer to the sun, we would also be spinning faster. This is what I'm talking about. So if we can measure the rotation velocity, and we can measure the distance of the star to the center, we can build a map of how much stuff there is in this galaxy. Okay, so let's look at these 2 stars. This star is closer to the center of the galaxy than that one is, than the second star is. But the second star is also rotating around slightly more stuff, because it's not just rotating around the center, it's also rotating around like everything in everything else in its orbit, including the first star. So it's got more distance, but also slightly more stuff. So you expect those two velocities to be roughly comparable. But this third star is rotating at a much bigger distance, and it doesn't seem like it's gained too much in its orbit. So you would expect the velocity of that star to be a lot lower than these two stars, because it's not gained a lot of stuff, but it's gained a lot of distance. And this fourth star pretty much has gained no stuff in its orbit, but is further away, so you expect, again, that velocity to go down. So this is roughly what I would expect as someone looking at this galaxy. This is what I would expect its velocity to look like for these four stars. So you go out and you do this experiment, and this is what you find. You find that the velocity pretty much stays the same, even as you're going further out. So if your velocity is the same, and your distance is increasing, that means the stuff that you are orbiting around must be increasing also very steadily. But you see the stuff, it's over here. And it's not increasing between these two stars. So that means that there must be a lot of very heavy stuff that we can't see, that these stars are orbiting around. We have identified a large amount of invisible stuff. But, as I've previously mentioned, just because it's invisible doesn't mean it's dark matter. In fact, space is kind of dark, so it's really easy to not be able to see something. If you're not gigantic and glowing, almost certainly a telescope won't be able to see. So just because there's a lot of like normal stuff that is not glowing in space that would be able to constitute the mass of the galaxy that is not dark matter. It's not nearly as interesting. So, but I've also mentioned to you a way to identify normal things that are not actively glowing. So, what you do is you essentially do the same experiment as the gas cloud. You look for a background star, a star that's far away, and you look at the light coming from that star, color by color. And as that star is passing through, like an invisible gas cloud, it will absorb some of that light, the starlight that's coming to you at specific energies. So you, as an observer, will observe this rainbow band, but there will be specific energies missing from your rainbow. And from that, you can look it up on a table, and you'll find that this is what the color bands look like for helium. And you're saying, there is a helium gas cloud over there. And by measuring how much light has been absorbed, you can estimate how much helium there is. So now you've identified all the normal stuff that is glowing and all the normal stuff that is not glowing. And this is your current inventory of the galaxy. You have the disk. The disk has young stars and gas and is highly bright. And around that, in a way that's not visually obvious, is the stellar halo. There's old stars, globular clusters, gas clouds, a lot of things that are not quite as bright, a lot more sparse, but still there. All this is still normal stuff. But as far as we can tell, and as far out as it can go, this entire thing is surrounded in a big halo of heavy stuff that is not showing up in either the telescope or the color line experiments. So we have no idea what this stuff is. And this is the thing that we're talking about. We're not talking about the stars that we can't see or the stars that we can't see. We're talking about the stuff that is not normal. Okay, so recap, things that we know. Dark matter is heavy space stuff that doesn't interact with light. And the reason that we can identify the existence of something like dark matter is we can measure things like rotation curves in galaxies. We can't see dark matter, but we can, the gravity from dark matter can influence the trajectories of the stars, and we can't see the stars. So by measuring something that we can see, we can infer the distribution of something that we can't. And as far as we know, there is a giant halo of dark matter around pretty much every galaxy. Okay, so we're going